In this video, we're going to look at the relationship of rate constants and equilibrium constants. So we're going to take a simple ligand binding reaction where protein P and ligand L are reactants, and they combine to form the protein ligand complex PL. So there are two rate constants associated with this equilibrium reaction. The top one is K1 and the bottom one is K minus 1. So molecularity is an important concept to remember and review. So it's the number of molecules involved in an elementary reaction. In this equilibrium equation, there are two elementary reactions. So there's a forward reaction. So that's where the protein P reacts with L, the ligand L, to form the protein ligand complex. And the rate constant for this reaction is little k1. The second elementary reaction is the reverse reaction, and that's where the protein ligand complex dissociates into its constituents, which is again the protein P and the ligand L, and the rate constant for this reaction is little k minus 1. So the molecularity of the forward reaction is 2. So there are two reactants, and so you just count them. And since this is an elementary reaction, the molecularity is equal to 2. The molecularity, by contrast, for the reverse reaction, the reactant is only the protein ligand complex, so there's only one reactant, and so the molecularity is 1. Okay, so remember that these are, for this we have the association equilibrium constant, so this is big Ka, okay, and that's equal to little k1 over k minus 1, a little k minus 1, or we can also express this as law of mass action, where the concentration of the protein ligand complex over the individual concentrations of the protein concentration times the ligand concentration. And remember, as we discussed before, Ka is the inverse of Kd, which is the dissociation equilibrium constant. So now back to the, when we're talking about rates versus rate constants, okay, those are different, all right? When we're saying that there's a distinction between them. So rates has to do with what happens when you multiply the rate constant. So K1 and K minus 1 are rate constants, but when you multiply the rate constant by the concentrations of the reactants involved in that elementary reaction, you get the rate. Okay, so these are two different things. Now, this also plays out in the units. We can see a difference. So rates are measured in units of concentration per unit time. For example, molar per second is a rate. Okay, so for instance, we could think of the consumption of ligand, or the loss of free ligand in this equilibrium reaction versus time, and we would say, okay, a certain amount of ligand in concentration of molarity is lost per unit time, and that would be a rate. The rate constant, again, are these constants, little k1 and little k minus 1. So the units depend on the molecularity of the reaction. And so K1 for a bimolecular reaction, such as the forward reaction, is going to have units of per molar per second. So notice where the concentration is, it's in the denominator. The unit is in the denominator instead of the numerator, as we see for rates. Okay. And then for K2, which is a unimolecular reaction, it's going to have units of per second. So now notice, for instance, if we take K1, which has units of per molar per second, when we plug this in, we just think about units. We're going to have per molar per second times molar times molar. The final unit will be molar per second. And the same holds true for when we multiply K2 times the concentration of PL. The final unit for the rate will be molarity per second. And so if we have two rate constants with the same molecularity, so or have the same units, okay, we can say the larger the rate constant, the faster faster the reaction is. And that is how we can determine quantitatively, if we can quantify these rate constants, we can compare reactions between each other as to which one is faster and which one is slower.